So the method that we're going to use to incorporate more experiments was called by Flageolet and Martin stochastic averaging. So what we want to do is, for some number m, the larger m is, the more accurate we'll get, we want to perform m independent probabilistic counting experiments and then average the results. So one thing you might think is, well, just use m different and independent hash functions. Well, that's no good because it's much too expensive. We can barely afford one hash function. It's just too expensive and wasteful. Another way to think you might try is to, when you get the data, just switch from one experiment to another. So that is, the first one goes into the first stream, divide into m streams. First one goes into the first stream, second one into the second, and so forth. That one doesn't really work because for certain inputs like this one, you might get really bad results. This stream has 4 different values, but they wind up all in the same stream, each one having 1 different value. And if you average those, you get 1 when there's actually 4. So that's not a good solution either. So what Flageolet and Martin said, use this idea called stochastic averaging. And then what we're going to do is we're going to use a second hash function to divide the stream into 2 to the little m, or big M, independent streams. It's kind of like a railway switching yard where the hash value determines what stream that you go into. And the key thing is that equal values all go into the same stream. So it's a proper way to divide up the stream into substreams for the purpose of cardinality counting. Then we do cardinality counting on these streams and average the results to get we expect that each one of them is going to have about the same number of distinct values as the original. That's stochastic averaging. So we'll use probabilistic counting on each one of those streams. So that way we get 2 to the m sketches. And then we average the number of trailing bits in the sketches, the little r value, and then return 2 to that mean divided by 0.77531. That's probabilistic counting with stochastic averaging. And then this is a trace of that. So an easy thing to do is whatever the hash function is, use the first couple of bits to decide which stream the data should go into. So this is m equals 4, which is 2 bits. So if the first 2 bits are 1, 0, it'll go into stream 2, just addressed by that binary value 1, 0. It's got an r value, so that one gets updated. The next one is 0, 0, so it goes in the first stream, and that's the one whose r value gets updated. And then the next one, 0, 1, same r value as the first one, but it's in a different stream. Now this one with 5 trailing zeros, its initial 2 bits are 0, 0, so that value goes into the first stream. And then continuing in this way, we have 4 different streams determined by the first 2 bits. And then at the end, we have sketches, 4 different sketches, and the r values of those sketches are what matters. And then average those and take 2 to that power. That's your estimate of the number of different values. It's only a little bit more code. So we're going to convert the stream into integers and compute r values right at the top here. And then what we'll use is a second hash, that's the value k, to determine, to split it into different streams. And that value k has a sketch value, and that's the one that the big R value gets ORed into. And then we just that's using the PC on each screen and get the sketches, and then we compute the average value, the trailing 1 bits in the sketches, and return 2 to that power divided by 0.77351. That's all in the original Flageolet-Martin paper in 1983. Now, what you observe is the accuracy improves as m increases. The question is by how much? And again, there needs to be a theorem, again, proven by Flageolet in the original paper, that says that well, it uses 64 M bits. That's for the different, if there's M streams, the 64 for each one. And it produces an estimate of the cardinality count with a relative accuracy close to 0.78 over square root of M. As M increases, it gets more and more close to the actual value. So that's our hypothesis, that the value is accurate to 0.78 over square root of M. And if we run it for 100,000 with M equals 1024, this is 10 trials. You can see we're really close to 100,000. And now our plot is, for all the trials, is pretty tight and pretty close to 100,000. That's a validation of the analysis. Another way to look at it is this plot, which shows the amount of space used, the value of M, versus the accuracy, the trade-off for PCSA. So the accuracy is 0.78 over M. As M increases, then the accuracy gets better. The bottom line is, say, with 64 32-bit words, we get 10% within 10%. And if we use a lot more bits, this is 1024 32-bit words, we get within 2.4%, which is really quite amazing that with a relatively small number of bits, the stream could be huge, remember, it could be billions. We can get quite close to the actual cardinality count with just that small number of bits. But we have to validate this, and again, we assumed that the hash function would work on our data. And one thing that's amazing about this 1983 to 85 paper is that it included extensive reproducible experiments. What they used was the manual pages for the computer that was in widespread use, so that everyone else could run their algorithm on these same data without even, there was no internet, so we couldn't really exchange data. Well, I can run it on my own data, this morning, and I run it and it's within 1%. If you want to know, is this algorithm effective? The answer is it's absolutely effective. So here's a summary of probabilistic counting with stochastic averaging. It's a demonstrably effective approach to cardinality estimation. You want to know about how many values are present in a given data stream? Use this algorithm. Makes one pass through the stream, uses only a few machine instructions per value, and with M words you can get within 0.78 over square root of M. Choose how accurate you want to get and how much memory you want to use. Those results have been validated through many different types of experiments over the years. Now, this is, even in the paper, they left open some questions. Can we do better in terms of space accuracy trade-offs? Maybe there's other operations that we might support on understanding the data stream rather than just counting the number of distinct values. This is a quote from the paper. It's quite clear that other observable irregularities on hash values of records could have been used. And it's important to recognize this because this paper really founded an area of research that has seen a huge amount of work on similar problems. We're going to talk in the next segment about a lot of different refinements. These types of papers are just examples of literally the hundreds of papers that have been written on data streaming algorithms, all starting from the Flageolet-Martin probabilistic counting with stochastic averaging research.